Welcome to today's video on identifying symmetry. It's important to remember that a figure in a plane has a line of symmetry if the figure can be mapped onto itself by reflection of line. You're familiar with lines of symmetry. So basically, line M breaks the image of this butterfly into half, and the image on the left could be folded over and map onto the image on the right. Map means lays on top of it with nothing overlapping on top or underlapping on the bottom. So here are some examples of some hexagons. This first six-sided hexagon has two lines of symmetry. This regular hexagon has 6 congruent sides and 6 congruent angles, which means it's going to have 6 lines of symmetry. This hexagon has 1 line of symmetry. It's important to note that a regular polygon will have the same number of lines of symmetry as sides it has. So a regular hexagon has 6 lines of symmetry. A regular octagon has 8 lines of symmetry. If I had a regular pentagon, it would have 5 lines of symmetry. And here are a few examples. This petal basically has 8 equal petals. It has 8 lines of symmetry. This starfish has 5 tentacles that all look the same. It has 5 lines of symmetry. This ram's head can only be divided with a line of symmetry down the middle. It has 1 line of symmetry. Next, we're going to talk about rotational symmetry. I personally feel like this image is a bad image, and what I would like you to try and do is think of it like it is 4 congruent parts. So they're all supposed to look congruent. I think it gets a little confusing here because on this figure, one side is curved and one side is aligned. But basically, if I took this figure and only turned it 45 degrees, this figure would not map onto this figure. It would be like sticking out there, 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 and there. So it's not considered to have rotational symmetry at 45 degrees. If I were to take this figure and rotate it 90 degrees or 1 counterclockwise turn and cut this image out and superimposed it over the original, there would be no overlap and no underlap. Same thing at 180 degrees. Now, if when it rotates 180 degrees, it's symmetrical, it's called point symmetry. But really what we want to talk about is rotational symmetry is anything that maps a figure onto itself by a rotation of 180 degrees or less about the circle. Okay? So when we turn this a fourth 90 degrees, it maps onto itself. It's called rotational symmetry. So let's look at this rhombus. This rhombus has 2 lines of symmetry. It also will not be mapped onto itself until it is at 180 degree rotation. And one of the ways, the shortcuts you can figure this out, because sometimes it's hard to look at it and see, is start with 360. They're seeing at 360 degrees in a circle. If I rotated something 360 degrees around its center, it would obviously match back onto itself. Figure out how many lines of symmetry there are. In this figure, in this rhombus, there's 2. 360 divided by 2 is 180. So this is 180 degree rotational symmetry. It maps onto itself. It also in this book is called point symmetry. And this octagon would have 8 lines of symmetry. 360 divided by 8. I'm doing this because some kids in the classes had troubles with it, is 45 degrees. That means that if I rotate this octagon 45 degrees, it's going to map onto itself. But also, every time I rotate it 45 degrees, it's going to map onto itself. So if I rotated it 45 degrees twice, that would be 90, or 3 times would be 135, or 4 times would be 180 degrees. So it actually is known to have rotational symmetry of 45, 90, 135, and 180. Once again, I did that by taking the 360 degrees in a circle or at a full 100% around rotation and divide it by the lines of symmetry. Now, some figures don't have rotational symmetry. Look at this trapezoid. Now, first of all, you don't want to get confused. These line drawings here are not lines of symmetry. They're just the diagonals of a trapezoid. This trapezoid only has one line of symmetry down the middle. It appears to be an isosceles trapezoid. 360 divided by 1 is still 360. So it does not have rotational symmetry because no rotation of 180 degrees or less maps it onto itself. Let's look at some more examples and you can try and solve these, but this rhombus has two lines of symmetry. So 360 divided by 2 is 180. It has 180 degree rotational symmetry. This octagon actually has 4 lines of symmetry. And if you're having trouble seeing those, it's there, there, and then through these. 360 divided by 4 is 90, so it would rotate at 90 and at 180 degrees. Would have rotational symmetry. This right triangle has no rotational symmetry. Now, a figure doesn't have to have 90 or 180 degree rotational symmetry to have rotational symmetry. It just has to be it has to be 180 or less. So for instance, this equilateral triangle has 3 lines of symmetry. 360 divided by 3 for 3 congruent sides is 120 degrees. It has 120 degree rotational symmetry. Notice that's not 180, but since it's less than 180, it's considered, well, not considered, it is classified as rotational symmetry. This rhombus, we keep talking about it, would have 2 lines of symmetry. That also means that it would have 180 degree rotational symmetry if I asked you to find that. This equilateral triangle, we said, has 3 lines of symmetry. So 3 lines of symmetry, 360 divided by 3 is 120. And this figure has 5 equal of these shapes. It has 5 lines of symmetry. 360 divided by 5 is 72 degrees. So it'd have rotational symmetry at 72 and at 144. Yes, if we rotated this, should be able to do this in my head, but 216 degrees, it would still map onto itself, but that's not called, we don't talk about rotational symmetry of a greater than 180 degrees, because if we rotated it around this way 3 times, that would be the same as 144 clockwise. Okay? Does this figure have rotational symmetry? No, it does not. These are not all congruent. These are different than this. So if it rotates, while this, if it rotates 120 degrees, would be mapped onto there, this is not going to map onto itself on the bottom. And I believe our homework on this one is 6 through 14.